Hello everyone, welcome back to my channel Shraddha's Physics. This video is based on statistical mechanics of the core 14. So today we will see the second part of the radiation pressure, that is the pressure of diffuse radiation. In the last class we have already discussed what is the normal incidence. So in case of normal incidence, so the radiation pressure we have already calculated, that is the pressure will be equal to the energy density in case of normal incidence. Normal incidence means the light will fall on the surface in the perpendicular direction. But in case of the pressure of diffuse radiation, the radiation will fall in every possible direction. So let the radiation is diffuse, that is the photons move in all possible direction. Let the incident beam of radiation, it makes an angle theta with the normal to the surface Lm. So you can see this is your Lm surface and it makes an angle theta with this normal direction. Now the energy incident on the surface scale, this is another surface, that is scale per unit area per second, that will be equal to this U into C, the energy. This is the energy density times the velocity of light. Now if S is the surface area of the plane KL, then the energy incident on the surface scale in 1 second, that will be equal to the total surface area. If I will consider this is S, here you can see that this KL surface is your S and this ML surface is your S prime. So for this surface scale, so that will be equal to UC into S, but the surface area of the plane KL, that will be equal to, here you can see that this is your angle theta, this angle is theta and this is your S prime. So this angle, this side will be equal to, this will be equal to S prime cosine theta. So this S will be equal to S prime cosine theta. Now if I will substitute in place of S, that is S prime cos theta, so that will be equal to, so the energy incident on the surface scale per second, that will be equal to UC into S prime cosine theta. This is clear. Now the total energy crossing Lm per second, that will be equal to the energy incident on Lm per second. This energy incident on Lm per second, that is also equal to UC into S prime cosine theta. So if we will calculate the energy incident per unit area of the plane, that is Lm per second, so that will be equal to this total energy incident, energy crossing per Lm per second divided by this total surface area of Lm. This will be equal to the energy incident per unit area of the plane Lm. Lm means this is your Lm surface, okay. So this will be equal to UC S prime cosine theta divided by, that is your S prime. So S prime get cancelled, that will be equal to UC into cosine theta. Now we will calculate the momentum incident on the surface Lm per unit area per second. So you know this is the pressure, that is equal to UC cosine theta divided by C. Here the C get cancelled, so that will be U cosine theta. So this component of this momentum in a direction normal to the surface Lm, that will be equal to along this cosine theta component. So this will be U cos theta into cosine theta, that will be equal to U cos square theta. This will be equal to U cos square theta. For diffuse radiation, the n beams of radiations meeting on the surface. So we know in case of the diffuse radiation, the photons will come in every possible direction. So the total radiation pressure on the surface, that will be equal to sum over U cos square theta. So this will be sum over U cos square theta, because in a direction normal to the surface, this is U cos square theta. So for every possible direction, that will be sum over U cos square theta. Now let us consider a hemisphere of, this is your radius small r and it have the center O. If we will consider a ring shaped AB or CD, this is your AB and this is your CD, it is cut from the hemisphere, then the area of the ring will be, if I will draw this diagram like, this is your, suppose the hemisphere, this is your, suppose the hemisphere and this is your some normal direction and this is your the radius small r, suppose we are considering this as your small r, and it makes an angle, this is your, if I will cut a very thin ring here, so it will be like, suppose for this. Now suppose this is your suppose angle theta, and in between these two ring, suppose this is your angle d theta, this is your angle suppose d theta. Now you can see that if this will be your radius r, and this is also your radius r, and this is also your radius r, so now you can see that this will be equal to your r d theta, this will be equal to r d theta. Now if I will see, consider that this is your perpendicular and this is your angle theta. Now this side will be equal to r sin theta, this will be r sin theta, this is your r sin theta. Again if I will consider this ring, then that will be the area of this, sorry, circumference of this ring, that will be equal to, that will be 2 pi r sin theta. And again for this ring, this is the thickness of the ring, this thickness of the ring will be r d theta. If this is your r d theta and this circumference will be equal to 2 pi r sin theta, then the area becomes 2 pi r sin theta into the r d theta. So that will becomes 2 pi r square sin theta d theta. Clear? So here this will be 2 pi r square sin theta d theta. Now as n beams are considered to be uniformly distributed over the surface of the hemisphere, so the number of beam crossing through this area of the ring, that will be equal to half into 4 pi r square, that will be equal to 2 pi r square. Half because we are considering the hemisphere. Now this dn will be equal to this 2 pi r square sin theta d theta divided by this area 2 pi r square into the total number of beam, that is n. So by cancelling 2 pi r square with 2 pi r square, the remaining will be n sin theta d theta. The fractions of beam incident between this angle theta and theta plus d theta, that will be equal to this dn divided by n. So by dividing this n, that will be equal to sin theta into d theta. So the pressure will be equal to this fraction of beam into this u cos square theta, because you know this u cos square theta means the total radiation pressure on the surface. Now this will be dn by n is your sin theta d theta into u cos square theta, that will be equal to u cos square theta sin theta d theta. So for all possible rings within that hemisphere, this theta may vary from, this is your 0 to pi by 2, okay, this will vary from 0 to pi by 2. So that will be equal to P equal to integration over 0 to pi by 2 u cos square theta sin theta d theta. So taking u outside of the integration, that will be 0 to pi by 2 cos square theta sin theta d theta. P is u, P equal to u integration over 0 to pi by 2 cos square theta sin theta d theta, cos square theta sin theta and d theta. So now if I will put cos theta equal to x, so that will be taking the derivative of both sides, that will be minus sin theta d theta will be dx. Now if I will put this value here and putting this limit when theta will be equal to 0, cos theta will be x equal to cos 0, that will be equal to 1, and for pi by 2, when theta equal to pi by 2, this cos theta will be equal to 0. So here the limiting value, you can see that this integration limit varies from 1 to 0. Again putting this cos square theta here, this will be x square, and this sin theta d theta will be equal to minus of dx. Clear? So this will be equal to, so this integration from 1 to 0, So, inverting that limit from 0 to 1 and this negative sign taken as your negative of negative, that is your positive. So, this will be u into integration over 0 to 1 x square dx. So, the x square dx will be s cube by 3 over the limit 0 to 1, that will be 1 by 3. So, finally, the pressure will be equal to u by 3. Clear? So, here what we have seen, that the pressure of diffuse radiation, this will be equal to 1/3 of the total energy density. So, it means that in case of diffuse radiation, the pressure will be equal to 1/3 of the total energy density, whereas in case of normal incidence, P normal will be equal to the energy density, but in case of diffuse radiation, it will be 1/3 of the total energy density. So, this is all for today. This is all about your radiation pressure. Okay. If you like the video, you can give a like, and if you have any query, you can ask me in your comment section. You may share and subscribe to the channel. Thank you.